Okay, let's begin with today's lecture. We discussed about ionization energies. What are ionization energies? It is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to produce 1 mole of gaseous positive ions. Whenever we have to remove 1 mole of electrons from 1 mole of gaseous atoms, it is important that you write 1 mole with 1 mole of electrons and 1 mole of gaseous atoms to form 1 mole of gaseous positive ion. These 1 moles are very important. If you just miss writing 1 mole, then surely he will deduct your marks. And in terms of equation, how can you write the equation? Sodium, 1 mole of sodium gaseous atom. On the left hand side, is 1 mole of electrons removed and it has formed 1 mole of gaseous sodium positive ion, right? So today we have to study these ionization energies separately. If we see the first equation, this first equation actually represents the first mole of electrons that have been removed from the gaseous sodium atom. So this first equation actually gives the ionization energy, or it is also known as first ionization energy of sodium. And when you have to remove the second mole of electrons from the sodium plus 1 gaseous sign to produce sodium plus 2 gaseous sign, this represents second ionization energy. Similarly, when you're going to remove 1 more mole of electrons from 1 mole of gaseous sodium positive 2 ion to form sodium positive 3 ion, then this is known as third ionization energy. So we need to define them separately as well. So first we will write the definition of first ionization energy, then second ionization energy, and third ionization energy. First ionization energy is, it is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous positive 1 ions. Or we can just simply write 1 mole of gaseous plus 1 ions. So this definition is exactly similar to the general definition of ionization energy. When you're going to remove 1 mole of electrons from 1 mole of gaseous atoms to produce 1 mole of gaseous positive ions. So this definition up till now is just similar to the definition of first ionization energy. Similarly, we can just try any other atom as well. Let's say if we have gaseous calcium atom, and if we're going to remove 1 mole of electrons from 1 mole of gaseous calcium atom, we will get 1 mole of gaseous calcium plus 1 ion. Similarly, if we have to remove 1 mole of electrons from 1 mole of gaseous positive, or we can say, we can also take 1 mole of gaseous chlorine atom. No, for negative ions, we are not actually removing the electron. We are adding the electron. And whenever we have to add electron, that's not ionization energy, that is called as electron affinity. That is another concept. So right now, we have just to remove the electron, and we are providing energy to remove the electron. For example, a gaseous chlorine atom, it always gains electron whenever it reacts. However, right now, we are removing the electron by force. We are providing the energy and we will remove the electron from the nuclear pull of chlorine. So chlorine atom will form chlorine plus 1 gaseous ion. I know it is unusual that you have always seen chlorine as gaining electrons, but right now I am removing the electrons from the gaseous chlorine atom by force to form gaseous chlorine positive 1 ion. So all of these equations, they represent the values of ionization energies, or rather the first ionization energies of these particular atoms. So the first equation represents the first ionization energy. I am writing ionization energy as IE in short. This is first ionization energy of sodium. Second equation is the first ionization energy of calcium. This is the first ionization energy of calcium atom. And the last one is first ionization energy of gaseous chlorine atom. Basically, this is a type of a reaction, because we are writing it like a reaction equation. So it means this is a type of a reaction where energy changes are involved. So if I ask you that whether the values of first ionization energy would be positive or negative, they always have to be positive, because you are supplying the energy to remove the electron. So can we say that the values of ionization energies are always endothermic? Ionization energies are always endothermic. That is, you have to supply energy to remove the electron. And as it is a type of a reaction, so can we say that energy change of this particular reaction is also known as enthalpy change? So we can also write the values of first ionization energy of sodium as del H IE1. In the bracket, we will write sodium. Similarly, for calcium, that would be del H. Del H is the enthalpy change. I hope you guys remember what enthalpy changes are. It is the amount of heat energy absorbed or released per mole of a substance. Right now, you are supplying energy for 1 mole of sodium to remove 1 mole of electrons to get 1 mole of gaseous positive ion. So for calcium, we can write this is the first ionization energy for calcium. And for chlorine, you can write this is the first ionization energy of chlorine. And these are the energies per mole of that particular gaseous atom. In future, if you need to remove 2 mole of electron from 2 mole of gaseous chlorine atom, then the values of ionization energies, if given, you can just multiply it by 2 to get the values for 2 mole of gaseous chlorine atom. And I can also show you these values if you just give me a minute. Let's just get done with the definition, and then we will go to the data booklet and we will see the values of first and second ionization energies of few elements. And how would you define second ionization energy? Can anyone just try to define the definition of second ionization energy? Second ionization energy would be when you are going to remove the second mole of electron from the same gaseous species. Once you have removed 1 mole of electron from a particular gaseous atom, you are left with gaseous positive 1 ion. But now when you are going to remove the second mole of electron, you will be left with gaseous positive 2 ions. It is the energy required to remove 1 mole of electrons from 1 mole of they have already prepared gaseous positive 1 ion. So now if you're going to remove the second mole of electron, that would be from the gaseous positive 1 ion. So it is the energy required to remove 1 mole of electrons from 1 mole of gaseous positive 1 ions to form 1 mole of gaseous positive 2 ions. So the important points over here is you have to remove 1 mole of electrons again, but from 1 mole of gaseous positive 1 ions, not from the gaseous atom, to form gaseous positive 2 ions. Right? If you just try to write the equations for the second ionization energy, let's say for sodium, So for sodium, we have already written the equation for its first ionization energy. Its equation for the second ionization energy would now be, once you have prepared Na plus 1 gaseous sign, if you remove further 1 mole of electrons, you're going to get Na2 positive gaseous sign. If you are forming Na2 positive gaseous sign, it doesn't mean you are removing 2 mole of electrons, because you are forming Na2 positive ion from Na positive 1 ion. So it means you have already removed 1 electron. Now you are removing further 1 mole of electrons. So this is the second ionization energy of sodium, and we can write it like this. This is IE2 for sodium. Similarly, if I asked you to write the equation for the second ionization energy of chlorine, that would be, if you have a chlorine plus 1 gaseous sign, if you're going to remove further 1 mole of electrons, you get Cl2 positive gaseous sign. So this is the equation for the second ionization energy of chlorine. Why didn't, okay, Rida, actually, if you are forming positive 2 ion from positive 1 ion, so how many electrons you're going to need to remove? You just need to remove 1 electron, 1 mole of electrons, because the ion on the left hand side was already plus 1. Got it? And if you just write the definition equation for the second ionization energy like this, let's say if you start from calcium gaseous atom, and if you form calcium 2 positive gaseous ion, then by removing 2 mole of electron, then this is not the second ionization energy of calcium. This is the wrong equation. This is basically the sum of first and second ionization energies. Actually, we have to study them separately, because whenever any element or the atoms of the element, they go for a chemical reaction. So we are always interested about their enthalpy changes stage by stage. Let's say if a calcium atom forms a calcium 2 positive ion, it is not like it just directly forms a calcium 2 positive ion. First it loses 1 electron, then it loses the other electron. So we need to know what energy changes are involved at each stage. When the calcium forms plus 1 ion, how much energy is involved? And when the calcium forms plus 2 ion, how much energy is involved? Which gives us the better picture of a chemical reaction. So we need to know about the energy changes that are being involved at each stage. Otherwise, if a calcium has to form a 2 positive ion, why are we just not studying it from a gaseous atom to form calcium 2 positive ion? If I just give you an example, do you think calcium would be available around you in the gaseous atom? What is the state of calcium around you? How do you find a calcium atom? Is it available in gaseous form or is it available in solid form? Calcium is a metal, right? So whenever you find calcium at room temperature, it is always available in solid form. So if we have to convert a calcium atom to calcium 2 positive gaseous sign, so can we just do it directly? Of course, when we're going to supply heat energy to the solid calcium, a time will come when it will form calcium 2 positive gaseous sign. But what are the stages involved from calcium solid to calcium 2 positive gaseous sign? First, calcium solid will melt to form liquid or molten calcium. Then it will vaporize to form gaseous calcium. And once the calcium is vaporized, all the calcium atoms are then separated or isolated from each other. Now, if you keep on heating it, the calcium first will going to lose 1 mole of electrons to form calcium plus 1 gaseous sign. But if you further heat it, this calcium plus 1 gaseous sign will lose further 1 mole of electrons to form calcium 2 positive gaseous signs. Can anyone just tell me what is the type of energy or enthalpy change involved from converting calcium solid to calcium liquid? Yes. What are the energies involved? How would you call this energy? You must have studied it back in physics grade 11. What is this process actually? This process is melting, right? So do you have any idea what this type of enthalpy change or energy change used to be called as back in your grade 11? Nobody, seriously. It is in endothermic, but it used to have a very specific name. These are latent heats. This is latent heat of fusion. Then this is latent heat of vaporization. The energies that are involved while changing the state of any matter are known as latent heats. Remember? Have you ever heard of it before or not? Okay, good. Okay. So, but obviously, if we have to form a calcium plus 1 ion or calcium plus 2 ion, calcium won't be available to us in the gaseous form. It will always be available to us in the solid form. It means first we have heated the calcium to form liquid calcium. And after liquid calcium, we have heated it further to form gaseous calcium. So basically what we have done is we have actually supplied latent heats. But are we discussing about these latent heats in chemistry? No. But these are the energies that should be involved because we are more interested when the atom it reacts. So latent heats are obviously part of your chemistry, but we cannot say that when we have to study about it during a chemical reaction, we are just concerned with the ionization energies. So we are just trying to break all of these enthalpy changes and then we will study them separately. And when we have to understand the overall reaction, then we can consider everything. Getting my point? So it's better that if we just try to study the enthalpy change separately from each stage to each stage, and when we need to have an overall understanding of the reaction, we can study all of these enthalpy changes together. Okay. So how would you write the equation for the second ionization energy of calcium? It should be when 1 mole of electron is removed from 1 mole of calcium positive 1 ion to form calcium positive gaseous 2 ion. Right? Now just define, how would you define third ionization energy? Sarah, Faik, Rayan. Energy required to remove 1 mole of electrons from 1 mole of gaseous positive 2 ion to form 1 mole of gaseous positive 3 ion. Very good. It would be the energy required to remove one mole of electrons from 1 mole of gaseous positive 2 ions. Do not forget to write gaseous ions, gaseous positive 2 ion to form gaseous positive 3 ions. And if we're going to write the equation, let's say for chlorine, if you already have chlorine gaseous positive 2 ion, if you're going to further remove 1 mole of electrons, you will get chlorine gaseous positive 3 ion. Right? For calcium, it should be calcium 2 positive gaseous ion to form calcium 3 positive gaseous ion. Obviously, you have not seen calcium forming a positive 3 ion, but right now we are just removing the electron by force. So we can just keep on removing the electrons. A calcium atom has 20 electrons. We can remove all 20 electrons if we want, just by providing ionization energies. If we just keep on removing electrons from the calcium gaseous 3 positive ion, ultimately it will form calcium positive 4 ion, then 5 positive, 6 positive, 7 positive. It will go on. Got it? Okay, let me just show you the values of these ionization energies. If you see the values of first ionization energy of sodium, ionization energies are given in kilojoules per mole. It means you should know the energy values that are involved for 1 mole of sodium gaseous atom. For sodium, the value of first ionization energy is 494. For magnesium, it is 736. And for calcium, we were discussing calcium as well, right? So for calcium, it is 590 kilojoules per mole. If you see chlorine, the values of first ionization energy for chlorine is actually not given. So it will, no, it is given. It is 1260, right? So every element has different first ionization energy values. So it means there are some factors that will affect the values of ionization energies. Okay, now just tell me, if we see the atom of sodium, a sodium atom has 11 electrons. Its electronic configuration, if we just show the electrons of the quantum shell, it should be 2, 8, 1. Now this is the sodium atom with 3 shells. And when we are going to remove the first electron from the sodium atom, it has to be from its outermost shell, right? We have to remove this electron which is present in the outermost shell. So for first ionization energy, we will be removing electron from the outermost shell. And if we see let's say magnesium atom is similar to the sodium atom in a way that it also have 3 shells. Magnesium atom also have 3 shells, and we discussed that across the period size of atomic size decreases slightly. So magnesium atomic size should be slightly smaller than sodium. And if we make the electronic configuration of magnesium, this is 2, 8, 2. Now, if we have to remove the electron, we are actually fighting by the nuclear pole of the atom, because this is the nucleus which is positively charged, and it is the responsibility of the nucleus of any atom to hold its electrons. Electrons are negatively charged, so the nucleus of both of these atoms are positively charged, and they are responsible to hold the electrons towards itself. These nuclei of these atoms, they are exerting a force of attraction on its electron because these are positively charged, right? Thank you, Rhythm. So magnesium's nucleus is holding its electrons by attracting its electrons, and the sodium nucleus is also holding its electron by attracting its electrons. Make sense? So if we need to remove the electron or the first electron from both of these atoms, and if you see the nuclear charges, sodium has 11 protons in its nucleus, whereas magnesium has 12 protons in its nucleus. So what do you think, which nucleus is exerting a greater force over its electrons? Is it sodium or magnesium? Magnesium, right? So would it be easier to remove the electron of magnesium or sodium? For sodium, it would be more easier to remove the electrons, right? Why? Because it has a weaker nuclear charge as compared to magnesium. If I just show you the values of their ionization energies, for sodium, the value of first ionization energy is 494. For magnesium, it is 736. Yes, there is a difference. Magnesium's first ionization energy is greater as compared to sodium. For sodium, it is 494. For magnesium, it is 736. 494 kilojoule per mole and 736 kilojoules per mole. So why is that? Because magnesium has a greater nuclear charge. So there are some factors that will affect the values of first ionization energies. And what are those factors? Obviously, first one is nuclear charge. But if I just compare with you guys the first ionization energy of sodium and potassium, and let's say for magnesium and calcium. You guys know potassium has 19 electrons. If you make its electronic configuration, this is 2, 8, 1. So a potassium atom has how many quantum shells? 4 shells. If you just draw the electron of a potassium atom, it should be third shell has 8 electrons and the valence shell has 1 electron. Now for calcium, calcium valence shell has 2 electrons. Electronic configuration of calcium is 2, 8, 2 because total number of electrons are 20. If you see their nuclear charges, potassium has a nuclear charge because its number of protons are equals to 19 and number of protons for calcium is 20. Now just let me show you. What do you think first? You need to tell me. If we compare the values of first ionization energy of sodium and potassium, which value do you think would be greater? Value of first ionization energy of sodium or potassium? Do you think the first ionization energy of potassium would be greater or lesser than as compared to sodium? Potassium's first ionization energy should be greater than sodium. Rayan, that's what you are saying? It should be lesser than sodium. Okay. Lesser than sodium because there is an extra electron shell. Good. What about you, Rida? You are saying that potassium's first ionization energy should be greater than sodium. Pike, waiting for your answer. Let me just show you the value of first ionization energy of potassium. It is 418. This is, you are not supposed to remember these values, okay? It will be given in the exams. This is 418 kilojoule per mole. So the value of first ionization energy of potassium is smaller as compared to sodium. And why it has to be lower? Although you can see there is a greater nuclear charge with potassium, but still its value of first ionization energy is smaller. It means there is another factor into action. And what is that other factor? That is shielding effect. Did we discuss about shielding effect while discussing about the atomic sizes? Of course, we must have discussed about shielding effect, right? What is shielding effect? It is the repulsion on the outer shell electrons by the inner shell electrons. We were comparing the shielding effect of sodium and potassium, remember? And for potassium, the shielding effect is greater. Why? Because potassium atom has more number of inner shells. So although there are more number of protons in the potassium atom as compared to sodium atom, but due to the increased shielding, if we used to compare the sizes of the potassium atom, size of the potassium atom is greater because there are more number of shells. Secondly, there is greater shielding, although the nuclear charge is greater. Similarly, if you're going to understand about the ionization energies, you have to realize, although the potassium atom has more number of protons, so we were expecting its ionization energy to be greater as compared to sodium. Because when we were considering the same thing from sodium to calcium, I was saying that because there are more number of protons and there is just one more proton in magnesium as compared to sodium. But still there is a large increase in ionization energy from 494 to 736. However, from sodium to potassium, there is an increase in proton number which is much greater as compared to magnesium. From sodium to magnesium, it's just an increase in one proton. But as we can see from sodium to potassium, there is an increase of 8 protons. But still, the value of first ionization energy of potassium is lesser, although it should be higher due to the increase in nuclear charge. But there is another factor that is into action. From sodium to magnesium, was there a change in number of shells? No, there was same number of shells in sodium and magnesium. It means the shielding effect on the outer shell electrons in a magnesium atom was similar as compared to sodium atom, because a sodium atom has 2 inner shells. A magnesium atom also have 2 inner shells. But if you see the potassium atom has 3 inner shells. It means shielding effect has a greater significance when it comes to deciding the values of first ionization energies. Because increase in nuclear charge should be increasing the values of ionization energy. And increase in shielding, what do you think increase in shielding should do? Should it increase the values of ionization energy or should it decrease the values of ionization energy? Shielding, when it repels the electron away from it means it becomes easier for us to remove that electron. So it means we will need to supply a lesser amount of energy if there is a greater shielding. Getting my point? So if both increases, nuclear charge increases, it is trying to increase the ionization energy. But as shielding effect also increases, it tries to decrease the values of first ionization energy. And both of these factors, they are actually fighting with each other. And let me tell you, always remember, shielding always wins. Shielding's effect is always more significant as compared to the effect of nuclear charge. Got it? Effect of shielding is more significant as compared to the effect of nuclear pole. That's it. Even if you compare the first ionization energy of magnesium and calcium, again, there are greater number of shells. So what do you expect? First ionization energy of calcium should be smaller than magnesium. But first ionization energy of calcium should be greater than potassium. Let me just show you the value of first ionization energy of calcium. This is 590. So it is smaller than magnesium because there is a greater shielding effect. But it is greater than potassium. Why? Because in between potassium and calcium, they are same number of charge. So same shielding effect. But potassium has a greater nuclear charge. So what are those factors that will affect the values of ionization energies? You have to write these factors first. So we have basically two factors that will affect the values of first ionization energy. First one is, of course, the nuclear charge that depends upon number of protons. If any atom has more number of protons, it means its nuclear charge would be greater. And the second factor should be your number of shells, because if number of shells increases, shielding also increases. And moreover, the outer shell electrons become farther away from the nucleus. So basically it becomes easier. All in all, it becomes very easier to remove the electron from the outer shell. So we have these three factors that will affect the values of first ionization energies. Distance of the electron from the nucleus. Of course, if the electrons are farther away from the nucleus, their values of ionization energy would decrease. And when number of shells increases, shielding effect or screening effect also increases. When number of shells increases, shielding effect increases, so the values of ionization energies must decrease. And nuclear attraction. When number of protons increases, nuclear pull or nuclear charge increases, so values of first ionization energy increases. Nuclear attraction can also be called as nuclear pull, or it can also be called as nuclear charge. So these are three names for the same concept. Got it? If I just try to write it mathematically for you guys, ionization energies are basically directly proportional to the nuclear attraction and inversely proportional to the number of shells. Because when you're going to increase number of shells, shielding will increase and values of ionization energy would decrease. But if when you increase number of protons, nuclear attraction will increase and the values of first ionization energies will increase. Got it? And there is just a little explanation over here that we have already discussed. You guys want me to stop over here if you want to copy it? Otherwise, if you're gonna copy it later, we can continue with the lecture. You guys wanna copy? And did you guys get any notes or these class notes? Did I send it to you on the group? Did I send these notes on your group in last class? And you guys still do not have the access to the portal. You guys were supposed to keep messaging us if we just failed to send you the notes, because it's been long now. So I'm just sending you right away. Okay, meanwhile, if you have any questions, you may ask. Otherwise, we will continue. No questions. Okay. So there are two factors that will mainly affect the values of first ionization energy, nuclear charge and shielding effect. Now, if I just ask you, last time we discussed about the trend of atomic sizes across the period. If I just ask you to write an answer that how should the ionization energy values differ for first ionization energy value differ across the period. Basically, I'm just asking you to write the trend of first ionization energies across the period. So can you guys tell me how? Ionization energies increases across the period. Very good. I need explanation of it as well. Because the number of protons increases. Very good. What about shielding effect? It remains the same across the period. So the overall values of first ionization energies must increase. Great. What about down the group? What should happen to the values of first ionization energies down the group? Should they increase or decrease? Decreases as shielding effect increases. But nuclear charge also increases, doesn't it? But shielding overcomes it. Very good, Rita. That's what I was expecting to hear. So across the period, the values of first ionization energies increases, but down the group it decreases. Let me just include these answers in your class notes. So you need to remember these two trends, factors, and you need to remember what happens to the values of first ionization energies down the group. Down the group, first ionization energy decreases, although nuclear attraction increases due to increase in number of protons. But as number of shells increases, distance of valence electron from the nucleus increases. Also, the shielding effect also increases. So effective nuclear attraction decreases. What is effective nuclear attraction? Resultant nuclear attraction. Because one of the factors is trying to increase the ionization energy and the other factor is trying to decrease the ionization energy. So we have to see the net effect or the resultant effect of it. In chemistry, we try to use the word effective in place of resultant. Yeah. Or we just try to use the word overall effect. Overall nuclear attraction or effective nuclear attraction increases. But if it would be okay if you just write nuclear attraction increases, that would be acceptable too. Or if you just write shielding overcomes the increase in nuclear charge, that would be acceptable too. Right? Even if you just write shielding is more significant, that is also acceptable. But the more important one is you should know the trend of first ionization energies across the period. The values of first ionization energies increases across the period. And the answer that you just have told me is correct. Let me just give you a write-up for that as well. So first ionization energies across the period, they always increases due to increase in nuclear attraction. But number of shells stays same. So shielding effect stays constant. And there is an increase in nuclear. You can just use one word. It would be okay if you just use the word nuclear attraction. Otherwise, you can remember that instead of nuclear attraction, he can also write nuclear charge or nuclear pull. Nuclear attraction increases due to increase in number of protons. But number of shells stays same, so shielding effect stays same. It becomes difficult to remove the electron. Got it? Okay, if you just closely see the values of first ionization energy across the period, let's consider an example of period 3. Period 3 has sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. If we see their values, the first ionization energy of sodium is 494, for magnesium is 736. We have just established that across the period, the values of first ionization energy should increase, and they are increasing. If you see the first ionization energy of argon, which is the last element of period 3, and if you compare its first ionization energy from sodium, which is the first element of period 3, of course, there is a massive increase in the values of first ionization energy from sodium to argon. But we were expecting this trend to be exactly in a straight line. It should have kept on increasing from sodium to magnesium and aluminum and silicon and phosphorus, sulfur, chlorine, argon. But we can see there are two dips or two anomalies from magnesium to aluminum and from phosphorus to sulfur. So if you see from sodium to magnesium, its value is greater. But as we see, the first ionization energy of aluminum is 577 as compared to magnesium, which is 736. For silicon, it is still greater. For phosphorus, it is again increasing. But for phosphorus to sulfur, there is a slight decrease in the values of first ionization energy. From sulfur to chlorine, this is again increasing. And from chlorine to argon, this is again increasing. So do you guys have any idea why this is happening? It is an exception. Okay, what else? Group number maybe. Okay, of course it has something to do with the groups because phosphorus and sulfur are in different groups. Anything else? Sodium, magnesium, aluminum. Aluminum has an atomic number of 13. Magnesium has an atomic number of 12. You just have to consider the factors we just have discussed. We have discussed about nuclear charge and shielding effect. Is there an increase in shielding from magnesium to aluminum? Magnesium atom has 3 principal quantum shells. Aluminum atom also have 3 quantum shells. So there is no increase in the number of quantum shell, is it? Quantum shells are not increasing, right? But there is a slight increase in shielding if in aluminum as compared to magnesium. Because if we compare the electronic configuration of magnesium and aluminum, magnesium's electronic configuration is 1s2, 2s2, 2p6, 3s2. For aluminum, it is 1s2, 2s2, 2p6, 3s2, 3p1, right? So if you have to remove the first electron from the magnesium atom, you have to remove it from 3s2 subshell. But if you have to remove the first electron from the aluminum atom, you have to remove from the 3p subshell. And 3p subshell is actually experiencing a slightly greater shielding as compared to magnesium 3s subshell. Because if you see all the shells before 3s2, we have only 3 types of subshells. But in aluminum, if we see the subshells before 3p, we have 4 subshells and more number of electrons. So that's why the shielding on the valence electron in aluminum, or the first electron that need to be removed, is actually greater. The shielding is actually greater as compared to the magnesium. So it becomes slightly easier to remove the electron from the aluminum as compared to magnesium. But you're not supposed to remember this. Got it? Not supposed to remember this. It's just for the discussion because I have just shown you this trend. Otherwise, we will make just a straight line. So do not worry about it. Okay, see you guys tomorrow. Love is. I'm just sending you these notes on your group.